Hey, my name is John Broadwell, creator of the Serial Wombat open source project and a consultant at my company, Broadwell Consulting Inc. If you need help with a project, hit me up. Today we're going to be talking about the NEC infrared transmission protocol from a protocol perspective, which may be interesting to people who are interested in implementing it in their own system or have an academic interest in this. If you just want to be able to read or send infrared, there are a variety of Arduino libraries, and we'll be looking at the Serial Wombat REMCON board, which integrates all the hardware that you need into an I2C compatible interface. This video does not talk about the details of how to use the Serial Wombat library to drive this board. We're going to be talking about the technical details of NEC. So if you're interested in IR transmit and receive, I would definitely recommend you take a look at the Serial Wombat 8B REMCON board. It includes a Serial Wombat chip running the Serial Wombat firmware that can do the encoding and decoding of NEC protocol and make those available through an I2C connection. It's really convenient. It offloads a lot of processing from your Arduino or MicroPython or whatever, and also provides a universal interface that you can talk to over C# or MicroPython or Arduino. It has congruent interfaces for all of those sort of things. So this board is pretty convenient. It has onboard I2C pull-up resistors if you want to. It has an extra solder jumper that allows you to boost the output if you're at 3.3 volts or 5 volts so that you get the max out of the IR transmit LED. And there is also an IR 38 kilohertz demodulator available on this chip. There are solder jumper connections that allow you to designate it as any I2C address from 0x60 to 0x68. So again, these are available through a Kickstarter through March, the beginning of March of 2026, and will be available on Amazon sometime in the summer of 2026. When we talk about infrared remote control, we're really talking about 4 separate levels. The first level is the absence or presence of light, and that is invisible light, infrared, at typically about 950 nanometers. If you're picking out an LED, you want a sufficiently powerful LED that's right about 950 nanometers. The second is absence or presence of a signal. We call this modulation or a carrier wave. And this is how an IR remote works in a room that's already flooded with IR signals from the sun, from heat sources, whatever. This is how we say, okay, there is an absence or the presence of a signal. Third is the IR remote protocol. And in this case, we're going to be talking about NEC. Other manufacturers like Sony and others have their own protocols, which this is how we encode ones or zeros by the presence or absence of a carrier wave. And then finally, there is the interpretation of that remote protocol, which says, okay, all we're doing over the remote protocol is sending numbers back and forth. What do those numbers mean in terms of a button? You know, does number 10 represent volume up or down? Does it represent I'm setting a color on a WS2812 LED strip? Does it mean stop or play for a DVD player? What does that mean? These are the 4 layers that we'll be talking about. So let's talk about the first layer. You need an LED that can do 950 nanometers. And you can either drive that LED directly from an I/O port, or if you want more power, you can drive it through a transistor. Next, let's talk about the carrier wave. The carrier wave on an NEC protocol IR remote is 38 kilohertz, plus or minus a little bit. And so what that means is to indicate the presence of a signal, you need to turn that LED on and off at 38 kilohertz. And in the embedded systems world, there's a variety of different ways that you could do that. You can generate the 38 kilohertz directly through software using delays. Usually this requires assembly language. You can use one of the peripherals on your chip to generate a PWM at 38 kilohertz. Or you could use a 555 or similar analog timer that generates that 55 kilohertz for you and it along with a higher level protocol signal. And all of these have advantages and disadvantages in terms of hardware simplicity, the degree to which they interrupt your other software. For instance, if you're using the assembly method, you may have to say the only thing I'm going to be doing is recording or decoding the signal. If you're driving it using a PWM that you turn on and off on one pin, then you're going to have to be very careful with regard to your interrupts and make sure that you hit those deadlines close, and you're going to have to do that quite a bit while you're generating or decoding packets. If you're doing the AND system, then you're either burning a couple of separate pins on your microcontroller, or you have some external hardware like a 555 that's generating that carrier wave frequency for you. And there are advantages and disadvantages to all of these. In the serial Wombat chip example, we're going to be using an AND chip where we're going to generate the 38 kilohertz PWM on one pin and generate the higher level protocol on another pin. And that's because of the system architecture of the serial Wombat chip, which is designed with a bit streaming DMA in place already that runs at 57,600. That's really good for the high level protocol stuff, but doesn't match up with the 38 kilohertz carrier. And so that'll be how we make that today, but essentially any method can work. It's just you have to understand the trade-offs. In order to receive and decode IR remote control signals, a demodulator is necessary. This is almost always an external circuit or module and are frequently included in the 38 sensor big packs that you get and are readily available from a variety of sources. Again, you need to choose a demodulator for NEC protocol that uses 38 kilohertz specifically. These demodulators typically go low in the presence of a signal and sometimes are what are called open drain inputs, which means that they can pull a signal low but not high, in which case you need a pull-up resistor. This could be an external pull-up resistor, or it could be one of the pull-up resistors that are integrated into the port of your microcontroller. When sending digital data over IR, there is only a single signal, the presence or lack of a carrier. Unlike, say, I2C, where you have two separate lines, one of which carries a clock and one of which carries a data. And so for IR, the entire signal is indicated by timing. So then you get into the packet format, which is specific by manufacturer. And NEC at this point is by far the most common in the hobby space and, in fact, for a lot of professional applications. The cheap remotes that come with a lot of no-name electronics, your WS2812 light strip controllers, your trophy acrylic engraved things, lots of robots, your 37 sensor kit, all of those tend to be NEC protocol, and increasingly manufacturers, especially manufacturers that have started production in the past 20 or 25 years, tend to use NEC protocol. In my case, my TCL television and my Samsung television also are NEC compatible, which is awesome because it means that I can use my projects to either receive those remotes or I can control those devices using an Arduino or other device, particularly with my new serial Wombat REMCON board. NEC protocol is really pretty simple. It's the start of a packet followed by 32 bits of information and then a final end pulse. The packet is broken down into two parts, an address and a command. And in the old days, the address was only 8 bits long. You sent 8 bits of address, followed by the inverse of that for 8 bits as error checking. Then 8 bits of command, followed by the inverse of that for error checking. And that was your 32 bits. Then you'd send a final end pulse. Nowadays, most devices anticipate a 16-bit address. And so you send out the 9 millisecond start pulse, take a break for 4.5 milliseconds, then send out 16 bits of address information, least significant bit first. Then you send out an 8-bit command, and then you send out the inverse of that 8-bit command as error checking, followed by a final pulse. Every pulse that we generate with NEC starts with a 562 microsecond pulse, and then is followed by a variable period of time without carrier wave that indicates whether it's a 0 or a 1. In the case of a 0, we turn on the carrier for 562 microseconds, then turn it off for 562 microseconds before starting the next bit. For a logical 1, we turn the carrier on for 562 microseconds, followed by 1,687 microseconds of no carrier time. Then finally, after we've sent all 32 bits, we turn on the carrier again for 562 microseconds. after which we give a amount of time before we send out the next packet. Typical standard is that there are 108 milliseconds between the beginning of each packet. NEC also supports something called a repeat code, which is equivalent to saying the last packet again. And the reason this exists is that it allows the message to be sent much shorter. That doesn't increase the data rate, but if you think about a handheld infrared remote control, it significantly reduces the amount of LED flashing that has to happen, which then in turn allows you to make your batteries last a lot longer. If you picture a TV remote where you may be channel surfing and holding down a button, or increasing or decreasing volume where you're holding down the button for a period of time, it can cut the amount of battery usage to send that command significantly. And it may not seem like much, but that can be the difference between having to change the batteries in your remote every 2 months or every 4 months, which is something that really drives customer satisfaction in products if they don't have to change the batteries as long. To send a repeat code, you do carrier present for 9,000 microseconds. You turn the carrier off for 2,250 microseconds, and then turn the carrier back on for 562 microseconds. So let's take a look at a signal that I sent out through the serial Wombat REMCON board and then received back in through the REMCON board. This is one IR NEC packet followed by 5 repeat packets that we sent out. And so we can see we have 4 different signals that we're looking here. The TX is going out. This is the NEC protocol. And this is coming out on pin number 7 of the serial Wombat 8B board. Here is the carrier wave. If we zoom in, we can see that this is a wave that just goes up and down at 38 kilohertz. And this is on pin 6 of the serial Wombat 8B chip. So these 2 signals together go into the AND chip, which is on the REMCON board. And so we get the combination of these 2 signals that come out. And that leads directly to the transistor, which drives the LED. So this is what our LED output looks like. You can see if we zoom in, it is the combination of the carrier signal and the higher level logic protocol signal. And then that goes out and it's immediately detected, or I shouldn't say immediately, it is detected by the demodulator chip, and that's fed back in to pin number 3 on the serial Wombat chip. And we can see it's interesting, there's actually a little bit of delay. The analog circuitry inside of the modulator, a few pulses have to come through before it goes low. And again, we said most of these modulator chips indicate active low, and so you'd want to be able to invert that going into whatever logic processing. That in this case, a low signal indicates presence of a carrier, a high signal on the demodulation indicates absence of a carrier. And so if we go in here again, we can see here is the standard NEC protocol. About 9 milliseconds of pulse, about 4.5 milliseconds of lack of pulse, and then there is a pulse for, in this case, it should be 5.62. It's reading at 620. So there's a little bit of variance here. But you can see that there is a pulse followed by another pulse, followed by another pulse. Each of these pulses represent the beginning of a bit. Then we get the final pulse, which indicates the end of the signal. And then beyond that, then about every 108 milliseconds, then I'm sending out a repeat. Again, the repeat is 9 milliseconds of pulse, followed by 2.25 milliseconds of non-pulse, followed by the final 5.62 microsecond pulse. And there is a little bit of slop in these kind of things. They don't have to be super, super exact, but you want it accurate probably within a few percentages of the real timing in order to be happy. I don't know that there's a specific spec on that, but it works. I'm not going to go into all the software of how I encode or decode these. They are available in the IRTX and IRRX code files on GitHub that show the state machines that I created. Again, and these feed up through I2C to the Arduino libraries on the serial Wombat protocol that you can command from MicroPython or Python or whatever to offload all of this capability from your main microcontroller, so it doesn't have to worry about creating these signals or decoding them. They simply turn into cues that you access over I2C. So that's all we have today. I hope you learned a little bit about the NEC protocol. If you're looking at this at February of 2026, hop on over to the Kickstarter and pledge to the Kickstarter to get one of these new REMCON boards. If you're looking at this at summer of 2026 or later, these should be available on Amazon. So until we talk again, have fun and keep making stuff.